If you're still awake and in the mood for gentle discovery, you've come to the right place. Hello there, and welcome to Science of Sleep. Whether your day has been bustling or tranquil, make yourself comfortable as we delve into why hot things glow from ember-red coals to the white-hot cores of distant stars. If you find this soothing exploration engaging, please like and subscribe to Science of Sleep. If you have a moment to share, where are you watching us from, and what time is it there right now? Let me know in the comments. Begin with a single atom of iron. Its nucleus grips electrons in layered shells, like balconies on a high tower. At room temperature, those electrons hum quietly, each staying close to its floor. Add heat, and collisions jostle them upward to higher balconies. They cannot hover there forever. The moment they drop back, they release a photon, a parcel of light, whose color depends on the jump. One atom emits a ruby flicker, the next an amber flash. Millions more follow until the solid bar gleams red. Raise the temperature and collisions become fiercer. Electrons leap from loftier ledges and return with brighter photons that mingle into yellow and then white. To the naked eye, the progression looks smooth, but spectroscopes reveal a forest of colored lines, each shouting a story about the microscopic acrobatics inside glowing iron. By the mid-19th century, physicists realized that any object, whether metal, coal, or molten basalt, will radiate a spectrum dictated almost entirely by temperature, not material. This principle, called blackbody radiation, puzzled even the brightest minds because classical equations predicted infinite energy at short wavelengths. That paradox, ultraviolet catastrophe, forced Max Planck in 1900 to propose that light is quantist. His daring assumption birthed quantum theory and explained at last why a poker in the hearth glows the color it does. Hold that hearth image. Early human clans gathered around flames not only for warmth and cooked marrow, but for guidance and craft. Clay hardened best when it shimmered orange. Bronze poured safely when its surface turned greenish-white. Smiths learned through eye and instinct what Planck later proved by mathematics. Color is a thermometer that needs no numbers. Even today, glassblowers shape molten cylinders by watching the radiant hue shift between tangerine and honey. Trusting sight more than Many artisans cannot explain photon emission, yet their craft speaks fluent thermodynamics. Lift your gaze from forge to sky. Every star is a furnace, obeying the same rule. Cooler K-type suns glow pumpkin orange. Our mid-temperature, G-type sun shines soft gold. Blistering oat-type giants blaze bluish-white. Astronomers plot those colors against luminosity on the Hertzsprung-Russell diagram, reading stellar life cycles at a glance. When Betelgeuse in Orion dims or brightens, observers debate whether changes in its outer atmosphere mimic the cooling and heating of forge iron. Scaled to sizes vast enough to swallow Mars, color becomes cosmic cardiology, diagnosing fusion rhythms trillions of kilometers away. Closer to ground, civil engineers think about glow in reverse. Brake discs on airliners must endure 700 degrees Celsius without warping, yet glow no brighter than dull cherry so that heat sensors know when to spray coolant. Filament designers for incandescent bulbs spent decades alloying tungsten to tolerate over 2500 degrees, producing white light before filaments sublimed to ash. Though LEDs now dominate, tungsten lamps still shine in photography studios because their spectrum mimics midday sun. Bathing skin in tones our brains evolved to trust. Glow reveals its hand even in darkness. Thermal cameras translate invisible infrared photons into false colors your eyes can read. Firefighters navigate smoke. Doctors map blood flow under skin. Astronomers chart baby stars wrapped in dust. The same black-body curve Planck tamed guides the software palette, turning cool fingertips into blues and inflamed joints into wild yellows. Behind each pixel stands a cascade of electrons that leaped, fell, and flashed their temperature signature. Yet, glow is only half the tale. What if things too cold to shine? A living room sofa at 20 degrees Celsius emits photons, mostly beyond red, wavelengths large enough to slip between retinal molecules unnoticed. Night vision goggles stretch that long-wave light onto phosphor screens, letting soldiers spot breath rising from distant mouths. Arctic foxes can see just far enough into near-infrared to detect vole tunnels under snow, proving that evolution sometimes tweaks the thermometer for survival. Our curiosity ramps. Let the detail thicken a notch. Inside every glowing ember lies a statistical sea known as the Planck distribution. Shorter wavelengths climb ever higher in intensity as temperature rises, but the peak shifts smoothly from infrared to visible. At 1100 Kelvin, metal glows deep red. At 1600, it brightens orange. At 2500, it nearly blinds. Engineers use pyrometers calibrated to peak wavelengths to read furnace walls without contact. Speleologists dating cave fires, scraped carbon soot, and through Raman spectroscopy, estimate the ancient temperature by how graphite crystal lattice fluoresce. A forensic glow centuries delayed. There is also the eerie reverse glow, chemiluminescence, and though not driven by heat, these reactions borrow quantum jumps to emit cold light. Fireflies oxidize luciferin, deep-sea comb jellies spark blue upon touch. Forensic teams spray luminol on crime scenes to reveal hemoglobin traces. Heedless glow proves that electron transitions need not always wait for furnace coals. Chemical energy can lift electrons to balconies, releasing photons on descent without warming the walls. Human technology copies nature. Glow sticks snap a glass vial of peroxide, flooding dye with energy. Rescue crews mark night paths with cold green beacons. In laboratories, researchers harness similar reactions as molecular reporters. Enzymes emit light, announcing that a target gene switched on inside a mouse embryo. The glow of life doubles as a notepad for experiments. But let us return to warmth. Picture the Sahara at noon. Sand so hot it appears white under polarized sunglasses. Grains absorb full-spectrum sunlight, then radiate back, mostly infrared, yet heat haze wobbles visible air, blurring dunes like thick glass. Physicists call the shimmering refractive index gradients, and model them with the same Planck curve applied to layers of differing density. A desert mirage, that phantom pool on the horizon, forms because your eye expects straight-line photons. Curved thermal pathways trick perception into thinking sky is water. Artists exploit this property in glass kilns, layering cobalt and silver nitrates to control emissivity. When cooled, the glass holds memory of its hottest hue, revealed under ultraviolet lamps as ghostly swirls. Museums date medieval stained glass by matching those swirls to kill recipes. Recorded by monks who likely never heard of electrons or photons indoors. Household incandescent bulbs once filled living rooms with a warm glow near 2700 Kelvin. An orange hue that lowered cortisol in evening and signaled melatonin that night approached. Modern LED bulbs mimic that. Spectrum through phosphor coatings, a technological homage to tungsten's dying filament. Sleep scientists now recommend programmable bulbs that shift from blue-rich dawn tones to deep amber twilight, reenacting daily temperature cycles of natural light that anchored hunter-gatherer circadian rhythms for millennia. As our part nears its crest, let one higher layer of precision join the tapestry. Quantum electrodynamics teaches that when an excited electron drops to a lower state, the emitted photon's energy equals the difference between energy levels. Multiply by Planck's constant and divide by wavelength. The math recovers color. Itself, blackbody glow, is merely the sum of countless electrons jumping between nearly continuous bands in hot matter. Yet in low pressure, gases' discrete lines dominate. Sodium street lamps bathe fog in monochrome gold, because sodium atoms prefer one specific electron leap. Neon spells crimson letters in city nights for the same reason. These spectral fingerprints let astronomers read the atmospheres of exoplanets. When a distant world passes its star, telescopes capture starlight, filtered through alien air, and identify sodium, helium, even water vapor, by their glowing lines. Tomorrow, when you switch on a stove coil and watch it redden, you witness the same physics, painting Jupiters, auroras, and forging gold in supernova shock fronts. Temperature writes color across scales unimaginable, and your eye decodes it instinctively. That instinct guided potters, poets, astronomers, and engineers, bridging craft and theory under one chromatic law. So, As the room cools and the night settles, imagine every glowing spark from stovetop coils to distant constellations, dimming by the same quiet law of color and heat, leaving behind a faint, reassuring afterglow that lingers in the mind like a soft ember, ready to kindle fresh wonder whenever curiosity stirs again. Imagine shrinking yourself until iron atoms loom like skyscrapers, and the space between them blurs into hazy twilight. In that twilight, temperature is nothing more mysterious than motion. When a bar of metal lies cold on a workbench, each atom merely quivers in place, the way people shuffle gently while waiting in a long queue. Add heat through hammer blows, coal embers, a spray of welding sparks, and those atoms begin to jostle like dancers pushed onto a crowded floor. Electrons perched on inner balconies feel the commotion, leap outward for the briefest heartbeat, then tumble back with a sigh of released energy. Each tumble sends off a photon, a tiny packet of light, whose color depends on how high the leap was. Millions of leaps overlap until the bar glows red. Crank the furnace hotter, and the leaps grow larger. The photons bluer, until yellow. Then nearly white light spills from the surface, like liquid dot. At the start of the 20th century, this simple glow baffled even the sharpest theorists. Classical physics declared that as objects warmed, they should pour infinite energy into the violet and ultraviolet. A prediction so absurd that newspapers mocked it as the purple disaster. A quiet Berlin scholar named Max Planck solved the riddle by suggesting nature works with indivisible rations of energy. Instead of a smooth sliding whistle, light emerges in crisp musical notes. Once Planck imposed those stepping stones, the predicted curve fit laboratory data with elegant precision. Long red wavelengths rose gently. A golden crest crowned the middle, and the high-energy violet edge fell away into darkness. Equation, though short enough to fit on a chalkboard, birthed the entire age of quantum science, and won him a Nobel medal hammered from metal that glows white before it melts, from Planck's curved tumble to guiding lanterns. The first, later named after Stefan and Boltzmann, says that if you double an object's absolute temperature, its radiance grows 16 times brighter. That rule sets the budget for everything from filament bulbs to rocket exhaust. The second, distilled by Wilhelm Wien, notes that the brightest color shifts steadily with temperature. Warm campfire coals sing deep red, molten bronze blazes orange, glass in a blower's pipe gleams honey yellow, and the surface of our sun, 5,500 degrees, when written in Kelvin, shines soft gold. Astronomers transcribe that gold into stellar family trees. Cooler dwarf stars glow pumpkin. Hotter giants flash silver blue, and each shade reveals chemical forges at work across millions of years. Every craft culture on Earth quietly mastered these rules, long before equations existed. Bronze casters in ancient Mesopotamia watched crucibles until the alloy turned the hue of apricots before pouring into clay molds. Song Dynasty potters judged kill readiness when the inside stoneware glimmered the color of duck egg yolk. 19. Blacksmiths tempered sword blades by shifting them through a rainbow of straw, peacock, and plum, each tint telling of precisely altered crystal grids inside the steel. No pyrometer can equal the practiced eye of a master, who has memorized the relationship between color and strength. Turn now to nature's grander furnaces. Along Iceland's mid-ocean ridge, lava fountains spatter a palette from dull garnet to dazzling persimmon as temperature slides a few hundred degrees. Far beneath, where mantle rock creeps slower than fingernails grow, pressure forces mineral atoms so close that conduction rather than radiation carries heat. Yet when a fissure forms, the melt rushes up, decompresses, and color blooms instantly. Volcano scientists film those flows with infrared cameras that convert unseen warmth into false color. Computer code then notes how the peak of the color curve slides each minute, giving clues to viscosity and gas content days before an eruption. Meteorites. 2. Reveal past glow. When a meteoroid hits our atmosphere, it shears against air molecules, heating its crust faster than water in a kettle. That crust melts, then refreezes moments later into a thin glassy rind called a fusion crust. Laboratories grind a sliver from that rind and fire a laser across it. The way atoms vibrate under the beam tells spectroscopists the exact shade the meteor once reached. A temperature history written like tree rings on a cosmic pebble. Glow does not belong only to flame and stars. City street lamps once bathed wet asphalt in the uniform orange of sodium. Because sodium atoms favor a single electron leap that spits out amber light with near military discipline. Neon sings crimson, mercury shouts icy blue, rare earth phosphors. Inside modern LED tubes, mix those disciplined colors into artificial daylight. Engineers trying to match the warmth of a living room filament have to sprinkle amber and red diodes, because a pure cold white light unsettles brains tuned through evolution to sunsets. Our circadian chemistry, guided by retinal cells that respond to sky blue, demands softer hues at dusk. Designers program bedroom bulbs to drift from pale Arctic morning through vanilla afternoon into cinnamon evening, reenacting Planck's glide in electronic disguise. Heat estates scale down to the silent realms too. A healthy laptop processor may hover near 80 degrees Celsius, invisible to eyes yet blazing in the near infrared. Thermal throttle circuits sip that glow through on-chip diodes, a microscopic nod to Planck, easing clock speeds if color threatens to wander beyond safe. Crimson. Far colder. A sleeping newborn's skin dwells just above 33 degrees. Pediatric nurses train infrared cameras on bassinets, the software painting cool blues over toes and reassuring peaches over cheeks, a quiet guardian built from blackbody lessons, lower still. At temperatures so near absolute zero that common metals turn into superconductors, light hides almost completely. Yet even their quantum restlessness forbids utter darkness. Experiments in helium-cooled chambers trap rubidium gas in intersecting laser beams. The atoms slow until momentum smears into a wave-like fog called a Bose-Einstein condensate. Cameras peer through windows frosted with liquid nitrogen and see hardly any glow. Yet mathematical fits still reveal a dim halo of long-wave photons. Proof that absolute stillness exists only in equations, between cosmic furnaces and quantum chill stretches. The everyday scale. When you preheat a ceramic baking stone, it passes through reds your eyes cannot resolve. Yet a cheap infrared thermometer, itself just a silicon chip, obeying Planck's curve, reads the flux and chirps once the number reaches ideal pizza territory. Lift the pie out, and the stone radiates upward, browning crust in seconds. Set a log on the hearth, and flames tuck their roots blue beneath orange tongues. Incomplete combustion sends cool carbon flickers aloft, before final oxidation wraps them in saffron veils. Flames read like weather maps once you know the language of glow. Not every glow requires heat. Glowworms on damp summer banks oxidize luciferin inside their abdomens. Jellyfish trailing gauzy bells near Mariana Trenches fire cold sparks at the flick of a tentacle. A forensic chemist spraying luminol finds a spatter path no human eye could catch. The scene lighting in ghostly turquoise as iron and hemoglobin catalyzes a chill photon cascade. Bioluminescence proves that electron leaps need not ride thermal plumes. Chemical intricacy can lift them high enough to fall as light without warming the stage. Technology follows suit. Emergency glow sticks crack a glass ampule, mix peroxide and dye, and bathe hikers in mint green halos through fog. Molecular biologists splice firefly enzymes into cancer cells, then track tumor spread in living mice by counting faint camera pixels. Cold light born in swamps and caves now guides scalpels and ambulances, yet hot light remains our cosmic heartbeat. Every sunrise pours quintillions of glowing quanta into chloroplasts, where green pigments politely reflect mid-range wavelengths and pocket the reds and blues for sugar work. Every evening city glass towers blush pink as steel, and concrete re-emit the day's harvest of infrared. Step outside at dusk, put a hand on a sun-warmed wall, and feel warmth leave as invisible light. Somewhere a chilled upper troposphere layer catches it, nudging water vapor toward cloud. Even the weather is painted by glow dot. Knowing this, you might watch your room tonight with fresh eyes. The faint red of a standby diode, the warm cream of a shaded lamp, the silver gleam on a kettle cooling after tiled trace arcs on the same graph Planck drew with trembling chalk longer than a century ago. Your retinas, your camera sensors, the night vision goggles of a patrolling ranger. Each device and organ in this chain serves as interpreter, reading color as temperature. Tomorrow, our exploration will turn to how digital chips snatch those photons, slice them into numbers, and reconstruct hidden heat on glowing screens. For now, let room shadows deepen while circuit boards and constellations alike exchange their radiant letters with the dark. Somewhere between ember and star, glow, hold steady, ready to write more stories and light whenever fresh questions appear. And now the glow itself grows more intricate as we examine the slender signatures known as spectral lines. Those narrow bands of color that emerge when atoms and molecules release light at precise wavelengths. In every glowing substance, from the hottest furnace to the faint mist of interstellar gas, electrons occupy well-defined energy levels. When an atom absorbs energy, whether through thermal collisions, electrical excitation, or photon impact, electron is promoted to a higher level. That elevated state cannot last indefinitely. And as the electron returns to a lower level, it emits a photon, whose wavelength corresponds exactly to the energy difference between the two states. The emitted photons form discrete lines that stand out against the broader continuum of blackbody radiation. Early investigators discovered these lines in flame tests, where salts placed into a Bunsen burner, flame produced vivid colors. Lithium compounds glowed crimson, copper salts shone blue-green, and potassium yielded a pale violet. Chemists soon realized that each element possessed a unique spectral fingerprint. In the 19th century, the development of diffraction gratings and prism spectroscopes allowed observers to spread light into its component wavelengths, revealing a forest of lines too thin for the human eye to distinguish without optical aid. Astronomers adopted these techniques to probe the composition of stars. By directing starlight through a spectrograph attached to a telescope, they recorded absorption lines, dark bands, where elements in a star's atmosphere absorb specific wavelengths from the underlying continuum. Each dark notch corresponded to a particular transition in atoms such as hydrogen, calcium, sodium, or iron. The discovery that distant suns share many of the same elements found on Earth revolutionized our understanding of the cosmos, establishing a chemical kinship between our planet and the stars. Laboratories now employ high-resolution EKL spectrometers, capable of resolving line profiles with precision better than 1 part in a million of the central wavelength. By analyzing line widths and shapes, researchers infer not only elemental abundances, but also physical conditions within the emitting medium. Broadening of lines can indicate high temperatures through the Doppler effect, while asymmetries betray magnetic fields via the Zeeman effect. In plasma physics facilities, spectroscopic diagnostics monitor ion temperatures and densities inside fusion devices, guiding efforts to sustain confined plasmas at tens of millions of degrees. Industrial processes harness these principles in real time. Steelmakers install optical emission spectrometers above molten metal vats to measure concentrations of alloying elements. As the liquid metal glows, atomic emissions of manganese, silicon, and chromium register on detectors. Operators adjust furnace parameters on the fly, maintaining the desired chemical composition without interrupting production. Glass manufacturers also incorporate inline spectrophotometers to track color consistency in molten batches, tweaking additive feed rates to achieve precise hues in flat glass, art pieces, or fiber optic preforms. Field geoscientists carry handheld spectrometers into remote locations. By analyzing ultraviolet-induced fluorescence or X-ray excited emission from rock surfaces, they detect trace elements that hint at mineral deposits. In planetary exploration, Mars rovers equipped with laser-induced breakdown spectroscopy fire pulses into rock targets, momentarily creating a plasma that emits bright spectral lines. The onboard camera spectrometer records those lines and transmits data back to Earth, helping scientists reconstruct Mars's volcanic history and search for past habitability. In environmental monitoring, spectroscopic instruments measure pollutants in air and water. Tunable diode laser absorption spectroscopy detects trace gases like methane or carbon dioxide by tuning a laser to coincide with a gas's absorption lines. As the laser beam passes through a sample chamber, the amount of light absorbed reveals gas concentrations down to parts per billion. This technique provides continuous, high-sensitivity measurements, crucial for tracking greenhouse gas emissions and informing climate policy. Biologists and medical researchers employ fluorescence, spectroscopy, and Raman spectroscopy to probe living systems. Fluorophores attached to biomolecules emit characteristic spectral peaks when excited by laser light, enabling visualization of dynamic processes within cells. Raman spectroscopy, which measures inelastic scattering of light, reveals molecular vibrations that correspond to specific chemical bonds. Surgeons use intraoperative Raman probes to distinguish healthy tissue from malignant tumors based on spectral differences, improving surgical precision and patient outcomes. Remote sensing. Satellites extend these methods to Earth's surface and atmosphere. Hyperspectral imagers aboard spacecraft collect reflected sunlight across hundreds of contiguous wavelength bands, generating detailed spectral cubes of land cover, vegetation, health, and water quality. Atmospheric sounders record thermal emission spectra in the infrared, mapping concentrations of greenhouse gases and profiling temperature and humidity layers. By comparing observed radiances to models of molecular absorption and emission, climatologists track seasonal shifts, detect volcanic eruptions, and monitor the recovery of ozone holes. Architectural lighting designers apply spectral engineering to create environments that support human well-being. By blending arrays of light-emitting diodes with different phosphor coatings, they craft fixtures whose spectral power distributions mimic natural sunlight at various times of day. Morning light, rich in blue-green wavelengths, stimulates alertness, while evening light emphasizes longer amber and red wavelengths that promote the release of sleep hormones. Such dynamic lighting systems help maintain circadian alignment in workplaces, hospitals, and residential settings. On the microscopic scale, materials scientists examine photoluminescence lines in semiconductor quantum wells and quantum dots. When excited by ultraviolet or visible light, electrons and holes recombine, emitting photons at discrete energies determined by quantum confinement. Measuring these emission peaks allows characterization of band gaps, defect states, and carrier dynamics in devices such as lasers, light-emitting diodes, and single photon sources for quantum communication. Art conservators use non-invasive, spectroscopic techniques to diagnose the condition of paintings and artifacts. X-ray fluorescence scanners identify pigment elements beneath varnish layers, guiding restoration by revealing original color palettes. Infrared reflectography exposes underdrawings and compositional changes. Ultraviolet-induced fluorescence highlights organic binders and previous retouching, ensuring that conservation treatments respect the artist's intent and preserve historical authenticity. In the realm of forensic science, investigators employ laser-induced fluorescence and Raman spectroscopy to detect trace evidence at crime scenes. Invisible stains of blood or gunshot residue become visible under specific excitation wavelengths, while Raman analysis identifies chemical compounds such as explosives, narcotics, or residues from explorants. The non-destructive nature of these methods preserves critical evidence for court proceedings. Even at the coldest end of the spectrum, spectral analysis remains indispensable. Researchers studying cosmic microwave background radiation detect faint fluctuations in temperature across the sky by measuring long-wave emission lines from hydrogen recombination during the universe's infancy. Those measurements constrain models of cosmic inflation and the distribution of dark matter and dark energy. Meanwhile, in cryogenic laboratories, scientists monitor blackbody emission from cooled silicon bolometers that detect single photons in millimeter wave bands, advancing the search for signatures of primordial gravitational waves. Throughout these diverse applications, the same fundamental principle applies. Electrons transition between quantized energy levels and emit or absorb photons, whose precise wavelengths form spectral lines. Those lines serve as universal diagnostics atomic barcodes that reveal composition, temperature, density, motion, and magnetic fields. Whether deciphering the glow of a blacksmith's forge, mapping the chemistry of distant stars, or diagnosing disease inside living cells, spectral lines illuminate hidden structures and processes with unerring precision. As this portion of our journey concludes, remember that every slender band of color you encounter, be it the crimson whisper of hydrogen in a laboratory lamp, or the pale signature of carbon in a flung nebula, carries within it the story of energy transitions at the heart of matter. Let these lines of light linger in your mind as silent narrators of the microscopic dances that shape our universe. And now, as the warmth of glowing matter fades from your vision, consider the subtle art of measuring temperature without touching a surface. Non-contact thermometry that reads the spectrum of emitted light to reveal heat from a distance. In industrial settings, pyrometers trained on molten metal or furnace walls gauge intensity of radiation at specific wavelengths, then convert those signals into temperature readings. By focusing on the peak emission wavelength, these instruments follow a principle first quantified by Wilhelm Wien. As an object's absolute temperature rises, the wavelength of maximum emission shifts toward shorter values. Thus, a glowing brick that appears deep red betrays a lower temperature than one glowing vivid amber. Engineers calibrate detectors to pick off that peak and compute temperature on the fly, ensuring steel pours, glass melts, and ceramic kilns maintain ideal conditions without ever touching a hot surface. Turn your mind to a steel mill's night shift, where glowing ingots roll past infrared cameras mounted on overhead cranes. Each camera splits incoming radiation into several bands: near-infrared, mid-infrared, long-wave infrared, then measures intensity differences to correct for emissivity variations caused by surface scale or alloy composition. Even slight changes in reflectivity can skew readings, so algorithms adjust using reference points built into the system. The result is a thermal map displayed on a screen, guiding operators to regulate cooling rates and avoid structural flaws. In that vast, echoing hall, the glow of metal becomes a living thermal portrait, a tapestry of shifting reds and oranges that technicians read like a weather forecast. Across the laboratory bench, a handheld thermal gun offers a simpler approach. Point and pull the trigger, and a small sensor sporting a germanium lens captures infrared photons. The sensor material converts heat into an electrical signal, which then undergoes amplification and filtering. A microcontroller processes the waveform, calculates temperature from the voltage level, and displays the result on a digital screen. You might use such a tool to check home radiators, restaurant grills, or automotive engines, relying on the same black-body relationships that govern suns and welding torches. Imagine a winter morning when frost blankets your neighborhood. Before dawn, your roof tiles radiate heat into the dark sky, cooling until dew freezes on their surfaces. A thermal imaging drone flying overhead sees patterns invisible to the eye: heat leaks from attic vents, gaps in insulation, hidden defects in window seals. Home energy auditors interpret those cold spots as invitations to retrofit, sealing drafts, and upgrading barriers. Every pixel on their handheld monitor tells a story of thermal loss. Each cool zone a whisper of wasted energy that, when addressed, translates into savings and comfort improvements. Delve deeper into the science of emissivity, the measure of how effectively a surface radiates compared to an ideal black body. Polished metals shine with low emissivity, reflecting much of their own glow back upon themselves and hiding temperature from infrared eyes. Black coatings, by contrast, approach unity emissivity, absorbing and emitting light nearly perfectly. Car manufacturers apply high emissivity paints to thermal sensor calibration panels, ensuring that test equipment yields accurate readings under variable conditions. Meanwhile, spacecraft designers choose surface materials based on emissivity and absorptivity. Balanced white ceramic tiles reflect solar radiation, while dark radiators on the spacecraft belly emit waste heat into the cold void. In the realm of meteorology, radiometers aboard satellites scan Earth's surface and atmosphere across multiple infrared channels. By comparing radiances at distinct bands, researchers separate contributions from surface emission, water vapor absorption, and cloud top temperatures. Algorithms invert those measurements to produce global temperature maps, monitoring sea surface warming, polar ice melt, and atmospheric trends. Operational weather forecasts incorporate these data, guiding storm warnings and climate analyses. In that giant silent dance, high above, glowing Earth speaks through its infrared voice. Shift now to the canvas of microscopic scales, nanothermometry. Based on luminescent nanocrystals, whose emission color depends sensitively on local temperature. Quantum dots engineered from cadmium selenide, for instance, emit green light at cooler temperatures, and shift toward yellow as they warm. Biologists inject these nanoparticles into living cells to visualize temperature gradients across mitochondria and membranes, revealing metabolic hotspots during cellular respiration. In that intimate theater, the language of glow once again deciphers the invisible workings of life itself. Consider ancient glassmakers, who long ago learned to judge kill heat by eye. They opened the furnace door and watched their creations glow, then gauged temperature based on the hue of the molten mass. Modern artisans still honor that tradition, using color charts that correlate visible glow to temperature ranges. When a silversmith anneals, a delicate filament, or a lampworker shapes an intricate figure, the artisan relies on that instinctive color-temperature link, honed through centuries of practice. In high-performance research, cryogenic experiments encounter the opposite extreme, very low temperatures where thermal emission nearly vanishes. Scientists employ superconducting bolometers, ultra-sensitive detectors cooled to fractions of a Kelvin to measure minute levels of infrared and microwave radiation. These devices convert absorbed photons into thermal pulses, which are then transduced into electrical signals. Bolometer arrays, aboard telescopes like the Planck Space Observatory, mapped the cosmic microwave background, capturing the faint glow left over from the Big Bang. There, in the frigid domain of early universe photons, glow becomes an echo of creation itself. Back in more familiar surroundings, programmable smart bulbs regulate both intensity and spectral composition. By blending red, green, and blue LEDs, they create a continuum of white light that replicates blackbody spectra at different apparent temperatures. Through wireless apps, users schedule gradual shifts from cooler morning light, rich in blue, to warmer evening glows, dominated by amber and red. That dynamic control aligns indoor illumination with natural circadian cues, promoting alertness in daytime and restful transitions at night. Even within your clothing, heat radiates outward and interacts with fabrics. Technical garments incorporate coatings and weaves designed to trap infrared emission and retain warmth. Phase change materials embedded in fibers absorb excess body heat by melting at specific temperatures, then release it as they solidify when you cool down. In such textiles, the principles of glowing spectrum inform material science, weaving comfort and thermal regulation into every thread. Throughout these diverse scenarios, from molten steel to living cells, from cosmic background to home comfort, the measurement and manipulation of glow-link technology and nature. Photons emitted by matter carry encoded information about temperature and composition, traveling across distances and scales without losing their story. By tuning our eyes, sensors, and instruments to that light, we unlock a universal thermostat that spans the forge, the forest, the laboratory, and the cosmos. Let us now journey from the realm of visible glow and infrared sensing into the domain of absorption, where matter seizes light rather than emits it. In laboratories and in nature alike, atoms and molecules intercept photons at specific wavelengths, leaving dark notches in otherwise continuous spectra. Those absorption features, whether etched in starlight that traverses an exoplanet's atmosphere or recorded by a smartphone camera lens filter, reveal the hidden constituents of the medium through which light has passed. When pure white light streams through a cool gas, atoms within that gas capture photons whose energies match the gap between two quantized energy levels. A hydrogen atom, for instance, can absorb a photon corresponding to its first transition, lifting its electron from the ground state to an excited orbit. That captured photon vanishes from the beam, and if enough atoms participate, a dark line appears at the hydrogen alpha wavelength of 652 nanometers. Extend this principle to complex molecules, water vapor, methane, carbon dioxide. Entire regions of the spectrum become dimmed or blocked. In astronomy, absorption spectroscopy underpins the study of planetary atmospheres and interstellar clouds. As light from a distant star passes through a planet's gaseous envelope during transit, molecules in that atmosphere absorb characteristic bands of starlight. Instruments like the James Webb Space Telescope record those bands as minor dips in the star's spectrum, enabling researchers to identify water vapor on temperate exoplanets, detect methane in cold gas giants, and even infer the presence of carbon-bearing compounds that may hint at biological processes. Each absorption trough corresponds to a molecular fingerprint, the unique set of wavelengths at which that molecule bites light out of the beam. Back on Earth, environmental monitoring employs infrared absorption to measure greenhouse gases and pollutants. Tunable diode laser absorption, spectroscopy, TDLAS, operates by scanning a narrow-band laser across an absorption line of the target gas. As the laser frequency sweeps, detectors record the intensity decrease at the precise frequency where absorption occurs. Scientists use that information to quantify concentrations of methane under leaking pipelines, carbon monoxide in urban exhaust plumes, and volatile organic compounds in manufacturing emissions. Because absorption signals scale directly with molecule count along the optical path, TDLAS instruments deliver parts per billion sensitivity without consuming sample gas across vast distances. Radio astronomers exploit absorption lines at microwave frequencies to probe cold interstellar clouds. Neutral hydrogen in the Milky Way absorbs the 21-centimeter radio emission produced by cosmic processes, painting dark features in sky maps that trace spiral arms and galactic structure. Similarly, free radicals and complex organic molecules leave absorption imprints against the bright background of distant quasars, unveiling chemical-rich zones poised on the threshold of star formation. In these studies, absorption demonstrates its power to reveal species that emit too faintly to observe directly on a smaller scale. Laboratory chemists apply ultraviolet visible absorption spectroscopy to determine concentration and purity of solutions. By measuring the attenuation of light at wavelengths where a solute absorbs most strongly its absorption maxima, they employ Beer-Lambert's law to calculate molar concentrations. Pharmaceutical companies adhere to these methods to ensure each tablet of a drug formulation contains exactly the intended dose. Food scientists measure color and nutrient content in beverages, inferring anthocyanin levels in wine or chlorophyll in vegetable extracts by their absorption characteristics. Biologists use absorption microscopy to examine living tissues. Brightfield imaging relies on variations in cellular absorption's cytoplasm, nuclei, and organelles differ slightly in their uptake of certain wavelengths, providing natural contrast. With staining techniques, specific structures take up dyes that absorb visible light, enabling pathologists to discern healthy cells from diseased ones. In recent advances, optogenetics harnesses light-sensitive proteins introduced into neurons. By illuminating brain tissue at particular wavelengths, researchers both visualize and manipulate neural activity with absorption-dependent precision. In oceanography, absorption coefficients of seawater inform studies of primary productivity. In carbon cycling, phytoplankton pigments absorb blue and red light for photosynthesis, leaving green wavelengths to penetrate deeper. Satellites equipped with ocean color sensors detect the ratio of blue to green light reflected from surface waters, estimating chlorophyll concentration across entire seas. Those data feed models of carbon uptake, helping scientists track how marine ecosystems respond to climate change. Industrial process control leverages absorption in quality assurance. In petrochemical plants, process analyzers measure sulfur dioxide and nitrogen oxide concentrations in flue gases using non-dispersive infrared sensors. These devices pass infrared light through extractive gas samples and measure absorption at narrow CO and CO peaks. Automated feedback loops adjust burner settings and scrubber chemicals to ensure emissions comply with stringent environmental regulations. In art conservation, multispectral absorption imaging uncovers underlying sketches and overpainting. Curators photograph paintings under ultraviolet, visible, and infrared illumination, then analyze absorption differences to reveal hidden compositions beneath surface layers. Infrared absorption imaging penetrates carbon-based underdrawings, while near can detect lead-white pigments beneath darker topcoats. These absorption-based insights guide restoration decisions without removing any original material. On the technological frontier, absorption phenomena empower novel sensing devices. Graphene and other two-dimensional materials exhibit strong, tunable absorption peaks in the terahertz to mid-infrared range. Engineers design ultra-thin photodetectors and modulators that exploit those absorption resonances for high-speed communications and chemical sensing. Meanwhile, metamaterials, artificially structured composite scan, achieve perfect absorption at selected frequencies, enabling cloaking devices and energy harvesting surfaces that trap light with unprecedented efficiency. Throughout these examples, absorption and emission stand as two sides of the same coin. Atoms and molecules exchange energy with light in quantized steps, sometimes releasing photons to glow, other times capturing them to vanish from view. By mastering both processized reading, emission lines that shine, and absorption features that hide, scientists decode the full story of matter and energy, uncovering secrets from the depths of living cells to the farthest reaches of the cosmos. Allow these lessons on absorption to deepen your appreciation of the unseen interactions between light and substance. In the darkness beyond direct sight, matter whispers its composition in every missing color, crafting invisible signatures that, once interpreted, illuminate worlds otherwise hidden. Let that realization settle within your thoughts, a silent echo of spectral interplay resonating as you drift toward sleep. And now we turn from the spectral dance of light to the intricate choreography of light's interaction with structured materials, optical interference, and diffraction, where glowing waves weave patterns of constructive and destructive overlap. When coherent light or thermal emission encounters thin films, gratings, or microscopic features, the resulting interference, fringes, and diffraction patterns encode information about wavelength, thickness, and refractive index. These phenomena underlie devices from rainbow-hued anti-reflection coatings to precision spectrometers, and even the iridescent shimmer of butterfly wings. Imagine a whisper-thin film of oxide on a bolt of surgical steel. Under incandescent glow, that film yields delicate bands of violet, blue, green, and yellow, each hue arising from reflections at the film's two boundaries. Light reflecting from the top surface interferes with light reflecting from the bottom surface. When those reflections align in phase, the intensity peaks at specific wavelengths, painting the surface in colored rings. Engineers exploit this effect to create anti-reflective coatings on camera lenses and glasses, tuning film thickness so that destructive interference cancels unwanted glare, while preserving transmission of desired wavelengths and laboratory diffraction. Experiments, scientists pass laser or broadband glow through narrow slits to produce characteristic fringe patterns on a screen. The spacing of those fringes relates inversely to slit width, enabling measurement of microscopic dimensions with astonishing precision. X-ray diffraction extends this principle to atomic scales. Powerful X-ray beams diffract through crystal lattice, generating spot patterns whose geometry reveals interatomic distances. Crystallographers reconstruct three-dimensional structures of proteins, minerals, and synthetic compounds by analyzing those diffraction maps, decoding the blueprints of molecular architecture that govern biological function and material properties on a grander scale. Diffraction gratings carved into metal surfaces disperse sunlight into rainbows in spectrographs aboard telescopes. In observatories, astronomers align gratings and cameras so that each order of diffracted light falls onto detectors, recording spectra of stars, nebulae, and planets. By calibrating grating spacing and blaze angles, they achieve resolutions high enough to detect minute Doppler shifts in stellar lines, uncovering exoplanets through the tiny wobbles they induce in their host stars. These precision measurements rely on the steadfast repeatability of interference across thousands of parallel grooves carved by ruling engines or holographic techniques. The natural world offers its own masters of interference. The scales of morpha. Butterfly wings comprise layers of cuticle spaced so that constructive interference amplifies blue wavelengths, creating a vivid angle-dependent shimmer that startles predators and attracts mates. Peacock feathers display iridescence through microscopic arrays of keratin and melanin rods, diffracting ambient light into shifting greens and golds. Some beetles harness multi-layer photonic structures to appear metallic under sunlight, a feature researchers mimic in creating structural colorants that never fade because they rely on geometry rather than dyes. Thin-film solar cells use interference to trap sunlight within semiconductor layers. By engineering layer thicknesses and refractive indices, designers enhance absorption at target wavelengths, boosting efficiency without increasing active material. Similarly, anti-reflective coatings on photovoltaic panels minimize reflection losses at air-glass interfaces. Each layer's optical thickness corresponds to a quarter of the target wavelength, causing destructive interference of reflected light and maximizing transmission into the cell. In this way, principles of glow and interference combine to harvest light for clean energy and fiber optic communications. Light pulses travel through glass fibers by total internal reflection, yet signal integrity depends on controlling mode dispersion interference between multiple propagation modes. Engineers designed fiber cores with graded refractive index profiles so that rays traveling longer paths move faster, equalizing travel times and maintaining pulse shape over kilometers. At repeater stations, optical amplifiers boost signal strength without converting to electricity, preserving the phase coherence required for dense wavelength division multiplexing, wherein hundreds of data-carrying wavelengths share a single fiber. Acoustic analogs of optical interference appear in phononic crystals, where mechanical waves encounter periodic structures, generating band gaps that block certain frequencies. But in optics, Bragg reflectors alternating high and Lindex layers reflect specific wavelength bands with high efficiency, functioning as mirrors in vertical cavity, surface-emitting lasers, VC, SELs, and thin-film filters in astronomy instruments. By stacking dozens of quarter-wavelength layers, designers achieve reflectivities exceeding 99% at selected colors, controlling glow within resonant cavities to produce coherent laser emission. On the microscopic scale, near-field scanning optical microscopy breaks the diffraction limit by bringing a subwavelength, aperture, or sharp tip within nanometers of a surface. The resulting interference between evanescent fields and scattered light reveals features smaller than half the wavelength, enabling imaging of semiconductor devices, biological membranes, and plasmonic structures with resolution down to tens of nanometers. Such techniques probe how glowing plasmons on metallic nanoparticles concentrate light into hotspots, enhancing fluorescence, spectroscopy, and enabling single-molecule detection in art and architecture. Designers use interference-based coatings to control building facades' appearance. Iridescent glass panels shift color with sunlight angle, enlivening skyscraper exteriors. Colloidal self-assembly techniques produce interference-based structural colors in ceramics and polymers, enabling durable, pigment-free finishes on everything from cookware to automobiles. These materials draw from the same physics that makes soap bubbles glisten, where variable film thicknesses create animated color patterns that delight the eye. Emerging metasurfaces push the boundaries further. Engineered with arrays of nanoscale antennas, metasurfaces impose prescribed phase shifts on incoming light, enabling flat lenses, holograms, and beam steering devices just a few hundred atoms thick. Such surfaces can manipulate thermal emission spectra, producing materials that selectively radiate at chosen wavelengths while suppressing others. Capability promising radiative cooling coatings that emit infrared glow into the cold sky yet reflect sunlight, passively lowering building temperatures. Through all these examples, interference and diffraction illustrate how the wave nature of light shapes the glow we observe and the technologies we build. By harnessing constructive and destructive overlap, from the ornate colors of a beetle's shell to the precision gratings of a spectrograph, scientists and engineers transform raw glow into patterns that convey information, generate energy, and enrich aesthetics. The interplay of light waves becomes a versatile tool, revealing structures from the nanoscopic to the astronomical. As you reflect on these layered interferences, consider the hidden architectures that color our world: microscopic films, periodic, lattice, and sculpted surfaces, all orchestrating light into purposeful glow and coloration. In that realization, the ordinary shimmer of dawn and the deliberate hues of engineered devices converge in a unified tapestry of interference, inviting you to perceive light not only as illumination, but as a medium sculpted by structure. Beyond the familiar warmth of glowing embers and the whisper of spectral lines, consider how light itself can be engineered to control temperature through radiative cooling and selective emissivity. In this realm, materials designed at the nanoscale emit infrared radiation more efficiently at specific wavelengths, shedding heat into the cold sky even under direct sunlight. Imagine painted panels on a rooftop that, while exposed to midday sun, remain cooler than ambient air because they radiate heat through atmospheric transparency windows. Those materials combine photonic structures and selective coatings to align their emissivity peaks with the 8 to 13 micrometer band where Earth's atmosphere is most transparent to thermal infrared. As a result, heat escapes into space, unimpeded, producing passive cooling without electricity or refrigerants. In laboratories, researchers fabricate multi-layer dielectric stacks and nano-patterned mesosurfaces that reflect visible sunlight while emitting strongly in the mid-infrared. By alternating layers of silicon dioxide and silicon carbide, by etching periodic arrays of holes in thin films, they create angularly robust emissivity profiles that outperform conventional paints. Field tests demonstrate temperature reductions of 5 to 10 degrees Celsius on test panels under blazing sun, validating models based on rigorous coupled wave analysis and finite difference time domain simulations. Those breakthroughs promise energy savings for buildings worldwide, reducing reliance on air conditioning and cutting carbon emissions. Turn next to photonic crystals, artificial solids, with periodic variations in refractive index on scales comparable to the wavelength of light. Three-dimensional photonic crystals, composed of polymer or dielectric spheres arranged in face-centered cubic lattice, exhibit photonic band gaps that forbid emission or propagation of light in selected bands. When tuned to the thermal infrared, those structures suppress unwanted radiative heat exchange, making ideal thermal insulators for spacecraft and cryogenic systems. By adjusting sphere diameter and lattice constant, engineers tailor the band gap location and width, achieving near total reflection of thermal wavelengths while allowing visible light transmission for windows that provide both insulation and daylight. In the realm of active devices, thermophotovoltaic generators convert thermal glow directly into electricity. A hot emitter, often a tungsten or ceramic surface heated to over 1000 Kelvin, radiates infrared photons directed toward a photovoltaic cell with a matching band gap. Selective emitters coatings or gratings on the hot surface narrow the emission spectrum to align with the cell's conversion efficiency, minimizing wasted photons. The photovoltaic cell then generates current as electrons absorb those infrared quanta and cross the pion junction. Such systems have achieved conversion efficiencies above 20% in laboratory prototypes and hold promise for waste heat recovery in industrial processes and hybrid solar thermal power plants. Materials scientists also explore glow at cryogenic extremes. Superconducting nanowire single photon detectors exploit ultrathin superconducting films, cooled below their critical temperature to detect individual infrared photons with near-unity quantum efficiency. When a photon with energy above the superconducting gap is absorbed, it locally breaks Cooper pairs and induces a resistive hotspot. That transient voltage pulse signals the photon's arrival, enabling applications in quantum communication, deep space, optical ranging, and single-molecule fluorescence spectroscopy. The detectors operate within dilution refrigerators at millikelvin temperatures, where thermal glow is suppressed and stray blackbody photons are filtered by optical baffles and low-pass filters. In optical computing, researchers harness thermal emission modulation for logic gates and neuromorphic architectures. Phase-change materials like vanadium dioxide transition from insulator to metal near 67 degrees Celsius, drastically altering their emissivity and reflectivity. By patterning thin films of vanadium dioxide on photonic cavities, engineers build devices whose optical and thermal properties switch state in response to electrical or optical stimuli. Those switches can route thermal signals or modulate radiative heat, laying the groundwork for chips that compute using photons and phonons rather than electrons. Even biological systems have evolved structures to control glow. Desert reptiles possess scale morphologies and pigments that reflect visible and near-infrared light to avoid overheating, while microstructures on moth eyes reduce reflection across a broad spectrum to provide stealth at both optical and thermal wavelengths. Marine organisms, like certain fish, exhibit multi-layer skin containing guanine crystals that act as angelin-dependent reflectors, protecting them from both visible predators and infrared-sensing prey. Biomimetic research draws on those adaptations to develop cooling fabrics and camouflage coatings that integrate spectral control from ultraviolet through mid-infrared. On the frontier of human comfort, smart textiles integrate microencapsulated waxes and phase-change materials that absorb latent heat when the wearer warms above a threshold, melting to store thermal energy, then solidify and release heat as the body cools. Researchers embed these capsules in polymer fibers and weave them into garments that dynamically regulate microclimate around the skin. Some advanced fabrics also incorporate thermochromic dyes that change color with temperature, providing visual feedback on thermal state, and when combined with selective emissive coatings, offering dual-mode regulation of heat through both radiative and convective pathways. In architectural design, cool roofs and vertical gardens employ principles of spectral engineering. White or light-colored surfaces reflect a high fraction of the solar spectrum, while specially formulated paints include infrared reflective pigments that minimize absorption of near-infrared radiation. Green roofs, with their vegetation and soil layers, combine evapotranspiration cooling with shading and insulating effects, further reducing building heat gain. Computational models for urban microclimates now incorporate radiative exchange calculations at city block scales, guiding planners to optimize materials, green spaces, and building orientations for maximal passive cooling. Finally, consider the vast expanse of space itself. Planetary scientists measure radiative balance on Mars, Venus, and Titan by comparing solar irradiation and outgoing thermal emission spectra captured by orbiters. Venus, with its dense carbon dioxide atmosphere and thick clouds of sulfuric acid, exhibits a strong greenhouse effect. Infrared emission to space originates only from high-altitude cloud tops, masking the planet's surface glow. In contrast, Mars's thin atmosphere allows direct radiation from surface rocks and regolith, enabling orbiters to map diurnal temperature variations and infer subsurface ice by observing thermal inertia. These interplanetary studies deepen our understanding of planetary habitability and inform designs for habitats that manage heat through tailored emissive surfaces. Throughout these varied examples, from rooftop coatings to cosmic observations, the mastery of glow and spectral control emerges as a cornerstone of modern science and engineering. By sculpting emission and reflection, we harness the fundamental interplay between light and matter to regulate temperature, generate power, probe invisible realms, and emulate nature's ingenious strategies. Each photon emitted or suppressed carries with it the imprint of these deliberate designs, whether cooling homes under the sun or revealing planetary secrets across millions of kilometers. As this seventh exploration draws toward its own quiet resolution, let these visions of spectral mastery settle into your thoughts, illustrating the profound impact of engineered glow on technology, environment, and our understanding of the universe. Soon, the warmth of these ideas will fade behind your closed eyelids, leaving a cool afterimage that guides you gently toward deep rest. And now let your mind drift into the microscopic world of glowing probes and quantum sensors, where the subtle emission of single photons reveals secrets at the scale of atoms and molecules. In the heart of a fluorescent microscopy laboratory, researchers introduce dye molecules that bind to specific proteins within living cells. Under gentle illumination, those dyes absorb light of one color and emit at a slightly longer wavelength. The emitted glow pinpoints the location and movement of molecular machinery motor proteins, hauling cargo along cytoskeletal tracks, ion channels opening to spark neural impulses, and enzymatic complexes assembling new strands of DNA. By capturing millions of these single photon events in rapid succession, super-resolution microscopes build images with clarity surpassing the limits of conventional optics, mapping life's processes with nanometer precision. Beyond biological imaging, scientists harness luminescent nanothermometers, colloidal particles, whose emission spectra shift with temperature changes of just fractions of a degree. These tiny sensors, often comprised of rare earth-doped crystals or semiconductor quantum dots, find their way into microelectronic devices to monitor thermal hotspots where transistors yield unwanted heat. In high-power laser systems, embedded Nanothermometers report on component heating in real time, allowing active cooling measures before damage occurs. Imagine a server farm humming beneath your floorboards, each blade of a cooling fan guided by data from invisible dots, no larger than a virus, collectively ensuring that the digital world runs smoothly without overheating. Consider to the realm of security and encryption, where quantum key distribution uses the particle nature of photons to guarantee unbreakable communication. A sender encodes a random key in the polarization states of individual glow pulses emitted by single photon sources. A receiver detects those photons with superconducting nanowire detectors, each count marking a bit of secret information. Any eavesdropper's attempt to intercept or measure the photons will inevitably alter their quantum state, alerting the legitimate parties to the intrusion. Thus, the delicate glow of individual particles becomes the bedrock of a new era of secure information transfer in environmental science. Glint and shadow patterns in satellite imagery map the spectral reflectance of land and water surfaces. Hyperspectral sensors aboard Earth-observing satellites capture hundreds of narrow spectral bands, revealing subtle variations in plant health, soil moisture, and mineral composition. Researchers exploit the faint near-infrared reflectance of healthy vegetation, known as the red edge, effect to track crop growth and detect early signs of drought stress. In deserts, the unique spectral signatures of different sand and rock types guide mineral exploration and archaeological surveys, uncovering ancient trade routes hidden beneath drifting dunes, diving into ocean depths. Bioluminescent creatures paint the night sea with ethereal light. From the gentle twinkle of plankton blooms to the sudden flash of deep-sea shrimps evading predators, these living glows adapt through evolution to communicate, lure prey, or confuse attackers. Marine biologists collect water samples and stimulate organisms under controlled conditions to measure emission kinetics and spectra. The data inform models of ecosystem health and carbon cycling, as the organism's glow signals variations in nutrient levels and water chemistry over vast oceanic expanses. Picture a research vessel at the equator, its dark wake shimmering with bioluminescent waves. Nature's own promise that life persists, even in the depths beyond sunlight's reach. In geology, the faint luminescence of minerals under ultraviolet light aids exploration. Geologists in the field wield portable UV lamps to scan rock outcrops for fluorescent minerals such as scheelite, which glows bright blue under long-wave ultraviolet. That glow betrays the presence of tungsten deposits below the surface, guiding drilling operations with minimal impact on pristine landscapes. Meanwhile, in diamond mines, sorting lines use UV fluorescence to differentiate gem-quality stones from industrial grit, each sparkle of undercut light marking potential fortune. On the cutting edge of materials research, scientists develop glow-in coatings that harvest ambient light and re-emit it gradually over hours. These long-persistence phosphors find use in emergency signage, glow-in-the-dark pathways, and safety gear for miners and first responders. By engineering energy traps within crystal lattice, researchers control release kinetics to match human perception, avoiding rapid afterglow decay, while preventing excessive brightness that could disturb dark-adapted eyes. Imagine illuminating a long underground tunnel with no power, yet guiding each step with a soft, sustained radiance born of daylight hours. In the domain of health and wellness, photobiomylation employs specific wavelengths of red and near-infrared light to stimulate cellular repair. Clinicians use LED arrays that glow at therapeutic wavelengths to accelerate wound healing, reduce inflammation, and alleviate pain in musculoskeletal injuries. The gentle glow penetrates tissue to modulate mitochondrial activity, enhancing adenosine triphosphate production and triggering protective signaling pathways. Patients lie comfortably beneath panels bathed in a warm crimson light, each pulse a subtle cue that biology itself can be harnessed for recovery. Returning to the cosmic scale, radioastronomers detect maser-emission natural microwave lasers in star-forming regions and the envelopes of red giant stars. Molecules like water, methanol, and hydroxyl amplify specific microwave frequencies through stimulated emission, producing intense narrow spectral lines that shine across interstellar distances. Observations of masers in our galaxy reveal sites of energetic outflows, shock fronts, and circumstellar disks. providing unparalleled insight into dynamic astrophysical environments. The faint hiss of maser signals received by radio telescopes tells of cosmic furnaces, where stars ignite and planetary systems take shape. In space technology, thermal control surfaces glisten with engineered emissivity. Satellites rely on coatings that reflect harmful ultraviolet and visible light, while radiating internal heat as infrared glow into cold space. Multilayer insulation blankets, composed of alternating layers of aluminized mylar and spacer fabrics, trap thermal radiation and minimize heat transfer. Precision black paints on radiators ensure efficient emissivity in critical bands, preventing onboard equipment from overheating or freezing in the vacuum of orbit, stationed hundreds of kilometers above Earth. These craft carry their own glow management systems, balancing energy and temperature amid the extremes of sunlight and shadow. Throughout these realms, from quantum optics to seafloor bioluminescence, from field mineral surveys to orbiting observatories, the thread of glow weaves a tapestry of understanding and innovation. The emission and absorption of light at all scales provide the tools to observe hidden processes, control environments, and enhance human life. And as your thoughts wander through these luminous domains, the quiet hum of photons and electrons continues without pause. Allow that ceaseless dance to lull you into stillness. Let each imagined glow from the pulsing lab microscope to the silent emission of distant galaxies fade softly behind your closed eyelids. If you enjoyed this serene exploration of light and rest, please consider subscribing to Science of Sleep. ***, good night, sleep well, and dream deeply.